Now we've got an enlarged picture of the change in velocity between point C and point D. On the original curve, we see that when we get to point D, the object is clearly, well, we can conjecture that the object is slowing down. So that at point E, it's going to be moving more slowly than at point D, which means that the vector at D is going to be shorter than the vector at C. And it's also still moving around the curve, changing direction as in the counterclockwise direction, so that the D vector, VD vector, will be counterclockwise from the VC vector. The delta VC will actually go from the tip of this vector to the tip of this vector, but I've offset it a bit just for clarity. Now what we want to do is we want to look at the delta VC vector compared to the average velocity vector over these two, over this interval. Now, if the velocity is VC at the beginning of the interval and VD at the end of the interval, we really don't know when the thing stops slowing down, or if it's slowing down linearly. It's probably not linear, so it's not completely valid. But if we add the VC and VD vectors, we get the VC plus VD vector, and half of that vector should be pretty close to the average velocity. So we're going to say the average velocity on the CD, I said, is equal to 1/2 of VC plus VD. I'll put that little wavy thing in there to indicate it's approximately equal. That's not a bad approximation, especially if the intervals are short. So we now have an approximation to the velocity, average velocity, V bar CD. And we can now sketch the delta V vector and the V bar CD vector and ask what they tell us. Okay? Now, in order to get a grasp on what these vectors are telling us, we're going to estimate the components of VCD parallel and perpendicular to V bar CD. So the change in velocity parallel and perpendicular to the direction of velocity. And we're making an assumption, just for numerical purposes, that the average velocity between C and D is about 7 on the scale, where before the length of this vector was 10. Now, under that assumption, I asked people to estimate the projection, or the components of the VCD vector in the direction of the average velocity. Again, the components of the delta VCD vector, the change in velocity vector, as parallel and perpendicular to the average velocity vector. So this vector, components of this vector, parallel and perpendicular to this vector. And what we came up with, well, I sketched another picture over here that doesn't exactly match this one, but you get the idea. So we got our average velocity vector here, our change in velocity vector here. How do we get the components? Well, to get the components, we simply project the average velocity vector on the change in velocity vector. We project the change in velocity vector on the average velocity vector. And we get the change in velocity parallel. Then we sketch a line perpendicular, dotted line perpendicular to the direction of our average velocity vector, and we project the change in velocity vector on to that direction. This gives us the parallel and perpendicular components of the change in velocity. Now, what's the significance of the parallel component of the change in velocity? Well, if our velocity is in this direction and our change in velocity is in this direction, what does that what does that tell us about the motion of the object? Well, it tells us that the object is slowing down. If the velocity is this way and the change in velocity is this way, it's slowing down. Or at least a part of the change in velocity in the along the line of the average velocity. Okay? So it basically means this is how fast we're moving on the average, and this is how much our velocity changes, so that the change in velocity being opposite to our average velocity tells us that we're slowing down. Okay? This is the magnitude of this vector is our speed. This is the change in our speed. and it's in the direction opposite to our speed. This vector tells us the change in velocity perpendicular to our direction of motion. Okay, it's like I'm driving and I'm maybe going around a curve. I might be slowing down as I go around that curve. That would be this situation where the change in velocity is in the opposite direction. The parallel component of the change in velocity is in the direction opposite to the average velocity, or to whatever my velocity is. But there's also a perpendicular component. Now it's going to the left, so maybe I'm going around the curve like this. And there's no need to change speed to change direction. Now this perpendicular component is going to change my direction. It's going to have no influence on my speed because this perpendicular component has no component in the direction of motion. Only this vector has a component in the direction of motion. So we see that we have the parallel component of the change in velocity, which affects speed, and the perpendicular component, which affects direction. If we want to calculate some indication of the force on this interval, well, if the path indicates the motion of a particle that has mass, then all we have to do is multiply the acceleration by the mass to get the force. And we see, I wrote it right here. First of all, the average acceleration parallel to motion is the delta V parallel to motion divided by delta T. We call that the tangential acceleration. Okay, that's the acceleration in our direction of motion. It will either this way in our direction of motion or opposing our direction of motion. The centripetal acceleration is the acceleration perpendicular to our direction of motion, and that's going to be calculated by taking the change in velocity in the perpendicular direction, the component of the velocity change in the perpendicular direction, dividing it by delta T. So that all this analysis gets us to a grasp on the parallel and perpendicular components of our acceleration. Then, if we have a mass, we multiply the acceleration by the mass to get the force. We have a force in our direction of motion. We have a force perpendicular to our direction of motion. Tangential force, centripetal force. Centripetal force causes the centripetal acceleration, changes our direction. Tangential force causes an acceleration in the tangential, an acceleration along our line of motion, either toward or away from our motion, and affects our speed. The board was slightly cut off because of the way I offset the boards. So let's just summarize real quickly. We got our velocity at C, our velocity at D. We find the change in velocity from C to D. We add the velocities at C to the velocity at D and divide by 2 to get our approximate average velocity between C and D. So here's our average velocity, here's our change in velocity. We can see intuitively that our change in velocity is more back, which means that we're going to be slowing down, and somewhat perpendicular, which means that we're going to be turning in this direction. We estimate components and so forth, but we look at this diagram, and what we do is we project the change in velocity on the direction of the average onto the average velocity vector. We get a vector back in the negative direction. The dot product of this with this will be negative, but the projection will be a vector in the direction opposite the average velocity, and the perpendicular component will be the projection of the change in velocity vector on a line perpendicular to the line of motion. If we divide the change in velocity by delta T, the change in the parallel component of the velocity by delta T, we're going to get the parallel component of the acceleration vector. And that's an average acceleration, and it's a vector, and I just noticed that there never was an arrow over that. Okay, so we get the average acceleration parallel to the incline and the average acceleration perpendicular to the incline. by, of course, dividing the change in velocity perpendicular to the incline by the time interval. And we call these the tangential and centripetal components of the acceleration. And those components can be multiplied by the mass of the particle or the object in order to get the centripetal the tangential or the centripetal force on the object or particle.